So in this section, we're going to look at Stokes' theorem, which is a 3D version of Green's theorem. And just to emphasize how similar it is to Green's theorem and how little there is that's different, I've got them written out next to each other. So let's just quickly review Green's theorem. Green's theorem says that for a region in the plane, and so this region should be like an open and connected, simply connected region, then the line integral of f dot dc around the boundary here should be, and so this is the circulation integral, right? This is computing the component of the vector field that is tangent to the curve. This is going to be equal to the double integral of the curl over the interior of the region, as opposed to Stokes' theorem, which says that if we have S now in R3, but it's important to say what I mean by S. What I mean by S is actually that it's a parametrized surface like this, not that it's a solid 3D region. So if we have a parametrized surface in R3, then the circulation integral, so f dot dc, so c here is the curve that's running around as the boundary of this surface that I've sketched out here. So the integral around that one-dimensional boundary of this curve is going to be equal to the double integral of the curl dot d sigma, which is the parameterization of S. Okay, and so in order to connect these exactly, I should point out something or clarify a lie that I told you earlier, and that lie happened right here. So I think I actually mentioned this at one point, but there's a little thing missing. That thing that I called the curl back in R2 wasn't quite actually the curl. It's what people call the K curl, or K component of the curl. So if we look at the meaning of this f dot dc integral, f dot dc, this is the integral of f dot the tangent vector ds, right? And so this guy, the meaning here is that we have in differential form p dx plus q dy. And then Green's theorem tells us that this is equal to the double integral over the region interior to C of the quantity dq dx minus dp dy. And that's with respect to d area. Okay, so the key fact is that this thing right here is not the curl of f, but it's the k component of the curl. So in other words, this is curl f dotted with k hat. So the curl of f, remember, is going to have three components. And so when I dot it with k hat, it's just going to pick up that third component and kill off the other two. And so what I need to have here to be honest about this is that this is k hat dA. All right, now it's legit. So let's see what the relationship is here between these two and why that should be utterly unsurprising. So if we could imagine this surface here as being parametrized by like the world's stupidest parameterization. Whoops. XY0, right? So this is, I'm thinking of taking R as a region in R2 and embedding R as the same region, but now as a subset of R3. Okay, and it's just got Z coordinate equal to 0. And if I did that, then as a parametrized surface, the unit normal vector to this surface would look everywhere like this one right here, pointing straight up with length 1. In other words, the normal vector everywhere is equal to k hat. Right? As opposed to if I'm off in like an honest 3D real world situation here of Stokes' theorem. I don't like that one. There we go. And in this case, and changes as we move around, right? There's all sorts of different things that the normal vector could be doing depending on how the surface bends. There we go. So over here, this is supposed to be an example of something that more looks like perhaps parameterized as the surface is a graph of a function. So maybe parameterized by sigma xy equals xy fxy. Okay, and so if we look just in general at a surface integral, then the integral over S of g dot d sigma is going to be the integral over S of g dot n d capital S, where capital S is capital S is the surface area element given by magnitude sigma u cross sigma v dA in some parameterization. That's this guy. So now in the special case, so if we have that S lives in the xy plane, as in this example over here, then this would be equal to, well, in this case, n is always equal to k, as I drew in the picture. And so that's exactly why we get from this one to this one. Or maybe vice versa. I guess we went from the general case to the specific case when the surface happens to live in R2.